Hi, welcome back to the second half of the final lecture for Math 310, Simon Fraser University, spring of 2020. So what I am doing in this last lecture, as well as the previous part, and I am solving the questions from the final exam from fall of 2017. It's not a particularly important choice. I just thought this provides a nice mix of review problems for you to try on your own, and then to watch and see how I solve them. And I'm also trying to make some comments about the types of methods you could use and the reason why we're doing certain things. So to lead you to see how you would solve the problem yourself. Okay, so here we are, questions. We've done questions 1 through 5 in part 1 of the lecture, and now we're going to do questions 6 through 10 in part 2 of the lecture. You will notice actually that there's quite a few questions on the Laplace transform on this final exam, and that is likely to be fairly similar on the final exam. It's a topic that hasn't been tested yet in either on the midterm, and it's an important topic, and it allows us to do things that we can't do with any of the other methods, in particular when we have discontinuous forcing functions. Okay, so here we're going to take a look at a function f, and is f and f prime, and they are continuous of exponential order. Okay, so this is important because a function has to be of exponential order for it to have a Laplace transform, and the continuity here is also important. Actually, you don't need it to be continuous, you just need it to be piecewise continuous, but anyways, something that's continuous is piecewise continuous, so that we are guaranteed, in fact, that the Laplace transform of f of t exists via those two statements. In fact, though, okay, that's fine. Okay, so what we're going to do now is we're going to represent capital F of S as the Laplace transform of f of t. And what this question is asking is to derive the formula that's given to you here, that the Laplace transform of, I see a prime is missing. Okay, the Laplace transform of the derivative of the function is s times the Laplace transform of the function. F of s is the Laplace transform of the function minus the function evaluated at 0. Okay, so how are we going to do this? We're told to derive the formula. So we have to go from, like, for example, we can't use the table. So what we're going to do is go from the definition of the Laplace transform. So the definition of the Laplace transform, it is an integral transform, and it looks like this. The Laplace transform of some function. In this case, I'm choosing the derivative because I want to find out what the Laplace transform of the derivative is. But for any function, the Laplace transform of the function is the integral from 0 to infinity of e to the minus st, and then whatever is here, f prime at t. So I mean, whatever function you have here, that function reappears here. So that right there is the definition of the Laplace transform. So what should I do now? Well, I mean, I don't know what f prime of t is. However, I can represent both its integral and its derivative, because I know that the integral of f prime is f, and I know that the derivative of f prime is f double prime. So I'm looking at this and I'm thinking to myself, okay, I'm going to it looks like a classic example of integration by parts, and I have to decide, should I assign u to be e to the minus st, or should I assign dv to be e to the minus st? And I am choosing to assign dv equals f prime at t because I do not see any advantage, and I do not see over here in the formula that I'm trying to show, I do not see the second derivative. So I don't want to assign u to be f prime at t, because then when I take the derivative, I'll get f double prime, and that just seems to be complicating the matter. I want to find the Laplace transform of the derivative in terms of the function. So it seems best to try to have dv equals to f prime at t, and that means I know what the integral of f prime is. It is f of t. Okay, and then we can assign the rest of the integral. That would be u would be e to the minus st and then I would differentiate that, and then du is minus s e to the minus st dt. Okay, so I'm going by parts, and I've decided to do it that way. So then I proceed with the by parts method, and I will be here. This will be uv e to the minus st f of t evaluated at 0 and infinity. That is uv minus the integral of v du. So v is f of t, and so v du, so I've got f of t, and I've got du, and I see it's minus s, so I'm going to put the plus there, minus s e to the minus st, and then I've got the dt. So now I have used integration by parts. Now I'm going to look at evaluating this, and then I'm going to carefully look and see what this integral represents. So now next step, Laplace transform of the derivative of t is the limit as t goes to infinity of f of t e to the minus st. That is the result of the integration evaluated at the upper limit infinity minus f of 0 e to the minus 0. That's the function evaluated, this thing here evaluated at the lower limit of integration 0. And then I have plus s times the integral from 0 to infinity of e to the minus st f of t dt. Okay, I can move the s outside. I've taken this s here and moved it outside like that because I am integrating with respect to t, and s is independent of t. So I can move it onto the outside of the integration symbol. Okay, now I'm down to 3 pieces, and I'm going to take a careful look at each one of them. The first one, well, this right here is 1, so that's going to be 1 times f of 0. I should sort of think, okay, that's good news. I see the f of 0 sitting right there. Now I'm looking at this. I need to evaluate this limit. Okay, but the key thing is that f of t is of exponential order, so it does not grow faster than this. And this thing here is exponentially decreasing. So this limit goes to 0. Okay, so this limit right here is equal to 0. That is because f of t is of exponential order. Okay, we cannot guarantee that that limit is 0 if f of t is, in fact, it won't be 0 if f of t it grows faster than exponentially. So that we would have to be, then we would be sort of stopped in our tracks. So that's why we have this condition on the function in order for it to have a Laplace transform. It's not a very strenuous restriction because most functions that are sort of we see physically are of exponential order. There's very few things in nature that grow faster than exponentially. Okay, next, so that has become 0. I see this piece that I want. The last thing to do is to take a look at this piece right here and see what this is. It's s times this integral here. And what is that integral? Well, that is the Laplace transform of f of t by the definition. So this piece right here is the Laplace transform of f of t. Good news. So then I have that the Laplace transform of the derivative is minus f of 0 plus s times the Laplace transform of f of t, which I have called f of s. So this is s f of s. Then I'm done. Okay, it's in a different order, but basically that is the result there. I've derived the result as required. Okay. Important derivation. So now you could do the same thing to find the Laplace transform of the second derivative using the Laplace transform. So, I mean, a good exercise for you would be to say, okay, let me try to show what is the Laplace transform of the second derivative, given I know this one, and I know that the Laplace transform of the function is equal to f of s. Can I do the same thing using the definition of the Laplace transform to find the expression for the second derivative. That's a good exercise for you to try. Yeah, you know what the answer is. It's in the table of Laplace transforms, so you can easily check your answer. Okay, next question. Find the Laplace transform for this function. Okay, so pause, momentary pause. This does not look like anything that we've really done before. We haven't found the Laplace transform of something that looks like this, a function defined like this. That's the first thing that is coming into my mind. And then the next thing that's coming into my mind is, how would I find the Laplace transform of that directly anyhows? I mean, this would be, I mean, so I'm just going to, this is not what you should do, but I'm thinking to myself, okay, it does not make sense to try to find it by the definition, because I'm thinking, what would this look like by the definition of the Laplace transform? It would be the integral from e to the minus st times the whatever function is here, and whatever that function here is this here. Okay, so that would be using the definition of the Laplace transform. That looks well, painful and very time consuming. You'd have to probably, I mean, you have to integrate this thing here, and you have to go by parts twice, and then you'd have to do another integral. No, this does not look like the right strategy. Okay, so like looks too time consuming. Okay. I'm looking at this function. I don't see anything like that. If I look now, how about the table? That would be another possibility. These are the ways I can get a Laplace transform from the definition, or I could look at the table and try to use, you know, shifting functions and this and that. Oh, maybe not. And then actually, it is sort of in but this is just I mean, this works, but it's not guaranteed. I'm looking at this thing here, and maybe that twigs you to think of the convolution integral. It does, of course, the variable of integration does not have to be tau. It could be something else. So, for example, we have been using tau, which is sort of a clue. But I mean, this function can be equally as well defined in this matter, t minus a squared cosine 2a dA. Okay, so it's a dummy variable, but still that is the one we've been using for convolution. And then what maybe the more important thing to notice is that we've got a sort of a t minus something, and then we've got a something, and we're integrating with respect to that something. So that might cause you to think about the convolution. Maybe somehow there's something here to do with the convolution integral. So that's the sort of thought process. Convolution integral. So then I'm thinking, what does that mean? Well, let's think. If I was going to do a convolution of two things, what would that be the convolution of? So I'm thinking this integral here, t minus tau squared cosine 2 tau d tau, is the convolution of t squared and cosine 2t. Okay? So if I took these two functions and let me label them. Let me just call this one g of t, and I'll call this one here h of t. If I gave you these two functions and I asked you what's the convolution of g of t and h of t, you would, I hope, produce that integral right there. So I see that it's the convolution of t squared and cosine 2t. And then that means that the Laplace transform of f is the product of the Laplace transforms of g of s and h of s. Now the problem is pretty trivial, because I can use the table to look up g of s as being 2 over s cubed with s greater than 0, and h of s, the Laplace transform of cosine 2t, is 2 over s squared plus 4, also with s greater than 0. So then I can easily write the Laplace transform of f of t, which is the product of those two things. So that is 2s over s cubed times s squared plus 4. That admits a small amount of simplification. 2 over s squared plus 4. And that is for s greater than 0. So I this is the most restrictive bound that I have in the two functions that I have there. Okay, so I want to be careful when I see something that looks a little bit unusual, that that I don't possibly proceed in a manner that's hugely time consuming and possibly error prone. I want to think, is there something that makes this a little bit more straightforward? Okay, that is convolution integral, the generalized multiplication. All right, a word problem. A spring with zero damping. Okay, I'm starting to read the question. A spring with zero damping, gamma equals 0, and unit mass, m equals 1, has natural frequency of 1. Okay, at time equals 0, the spring is completely stationary. Okay, time equals 0, the spring is completely stationary. What is that telling me? That is telling me the initial condition is at t equals 0. Yes, initial conditions are at, in fact, let me write it properly. Let's make this a little bit bigger. So I'll write it down here. So I'm on this sentence right here. It'll be sort of, I'm parsing through here, getting all the information I'm going to need to write down the differential equation, or in this case, the initial value problem. So I'm seeing I have initial conditions at t equals 0, and what are they? 0 displacement, 0 velocity. We have typically been using the variable u to indicate the displacement of a spring, so I'm just going to continue with that. I'm going to say that I've got u of 0 is 0 and u prime of 0 is 0. I've got the initial conditions, and external force is applied. Okay, so I'm going to see now that there is an external force is applied. F of t equals 1 until t equals pi. So now I'm just going to draw this so I can get a situation of what's happening. External force is applied, so I'm drawing f of t versus t. The function is so it is 1 until time pi, and then it is switches to -1. At time t equals 2 pi, it is turned off. Okay, so I have here 1 and -1. So I have basically, I shouldn't draw these as pi, just like this, like that. This comes down like that, and then I don't want to imply that there's values here, and then it switches like that. Okay, so I have a function that on the right hand side, this is my forcing function, the external function that's applied. We've been calling that the forcing function. Okay, so I'm thinking right now. I'm like, okay, I've got a piecewise continuous forcing function on the right hand side. I'm immediately thinking that I'm going to be using the Laplace transform. So at this point, coming into my head is Laplace transform, because none of my other methods will work with this type of forcing function. Okay, and now that I've made that decision, then I'm thinking to myself, next step would be then to represent f of t in terms of the unit step function. Okay, all right, so I will do that. Let's see what's happening. F of t will be 1 to start, and then at time pi, I could, if you want, multiply this by u0 of t, but that is not going to matter because the whole thing is starting at time t equals 0, and the thing is 1 at that point, so that is just going to disappear, but that's fine. And so then what happens at time pi? It has to go from 1 down to -1. That means I'm going to have to subtract 2 to move from 1 down to -1, and that's going to happen at time pi. And then at time 2 pi, that's right here is 2 pi. At time 2 pi, the function is going to have to be increased by 1 here. So I'm going to add that 1 in at time. So this is, wouldn't normally do this, but I'm adding in a 1 times u 2 pi of t. Okay, I'm just going to rewrite that like this, slightly simplified. That looks like this: 1 minus 2u pi of t plus u 2 pi of t. There it is. Okay. All right. So I've now handled this part here. In fact, I've handled it all the way to here. Write down an initial value problem that models the displacement of the spring. Okay. Write down an initial value problem. Initial value problem that consists of a differential equation and initial conditions. It's really be as careful as you can to read the question and answer what the question is asking. Okay, so I've already determined these initial conditions. That is, u of 0 is 0 and u prime of 0 is 0. What else? I need to recall the differential equation for the spring, and that looks like this. So I'm working on this part right here. As we saw through a variety of examples, the general differential equation for the displacement of a spring looks like this. Okay, where this is the mass, this is the damping coefficient, and this is the spring constant. So I'm already actually fairly a long ways a ways in being able to find out what to do here, and that is I know already that the mass is equal to 1. I know that the damping coefficient is equal to 0. I need the spring constant, K. Okay, what do I know? What else do I know? I know that the natural frequency is 1. Then we also know that the natural frequency is the square root of the spring constant over m. Okay, so m is 1. And omega naught is 1, so we have 1 is equal to the square root of k. So k is equal to 1. Okay, so now I have all of the pieces here, and I can write out the differential equation. I've already got the initial conditions, and that will give me the initial value problem. So let me just write the differential equation for this specific case. So this is the general case for the spring. This is for all single spring systems. This is the general spring differential equation, which we did hash over in pretty grisly detail during the lectures. And so now for this specific system, for this mass, this damping coefficient, and this natural frequency, the differential equation is u double prime. That's because the mass is 1. There's no u prime because gamma is 0. And then the k is 1, so this is plus u. And then we have the forcing function, which we have figured out. There we go. Okay, so we've got initial conditions and we've got the differential equation that gives us the initial value problem. So that's the differential equation, and then those right here are the initial conditions. Those two things combined are the initial value problem. Okay, now it is a matter of solving this differential equation with those initial conditions. And because of the forcing function on the right-hand side, I'm going to use the Laplace transform. Take the Laplace transform on both sides. Okay, so that will lead me to s squared plus 1 times the Laplace transform of the solution, and there's nothing else there because the initial conditions are 0. So this is I mean you can do it a little bit more detailed, but I mean you can see that the characteristic equation of if this were homogeneous would be this s squared plus 1. All the initial conditions are 0, so the other terms are gone, and then I'm taking the Laplace transform on the right hand side. The Laplace transform of 1 is 1 over s. The Laplace transform of 2 u pi of t is 2 e to the minus pi s over minus s, and then the Laplace transform of u of 2 pi of t is this one here, plus e to the minus 2 pi of s over s. So the Laplace transform on the right hand side, you can read those directly off the table, or if you wanted, you could get them from the definition of the Laplace transform. Clearly, using the table is the way to go for these straightforward ones like this. Okay, so that means that u of s is the Laplace transform of the solution is 1 over s times s squared plus 1 minus 2e to the minus pi s over s times s squared plus 1 plus e to the minus 2 pi s over s times s squared plus 1. Okay, I'm looking, I have the usual choice, partial fractions or completing the square. Clearly this is going to be partial fractions. It's already factored. So I'm going to do the partial fractions on this so I can see what's going on. S squared plus 1. So this is partial fractions. Partial fractions. Okay, so that's going to then be a over s plus bs plus c over s squared plus 1. S squared plus 1 is irreducible quadratic. Okay, so then I see that I have as squared plus 1, sorry, as squared plus a plus bs squared plus cs is equal to 1. That's make the denominators the same, so therefore the numerators need to be the same. So I end up with two equations here. Well, actually, I end up with a plus b is equal to 0. That is from on the square term. A plus b is equal to 0. There's no square term over here. Then I look at the linear term. The linear term is also 0, so c is equal to 0. And then I look at the constant term, and that is a, and the constant term over here is 1, so a is equal to 1, and that means that b is equal to minus 1. So I now know that this is 1 over s minus s over s squared plus 1. Okay, so I have 3 pieces of the Laplace transform. I need to now figure out the inverse Laplace transform. I want to figure out the inverse Laplace transform of this, and this. Okay, but notice they all have the same. I mean, they all have the same denominator, and you should recall that multiplying by e to the minus something is shifting the function in the time domain. So with that those thoughts in mind, I'm going to write out what the inverse Laplace transform is. So I know what the Laplace transform of the solution is. Now I'm trying to find what is u of t, the solution to the differential equation. That's what I want. And u of t is the inverse Laplace transform of u of s. And that is the inverse Laplace transform of those 3 things that I've boxed in blue there. And I'm going to write it like this. It's g of t. And g of t is, okay, let me just say what g of t is. G of t is the inverse Laplace transform of 1 over s times s squared plus 1. So it's that inverse Laplace transform of this first term here. And I'm doing that because I can see that I can represent the other 2 in terms of g of t. And then I'll have this whole thing written out, and then I just have to figure out what is g of t. And that's not going to be too hard because I already have done the partial fractions. Okay, so I'm going to just move this down a little bit. I see it's going to... So I'm writing here u of t, that's u of t, which is the inverse Laplace transform of u of s. That is going to be g of t, that first one. And then the next one is going to be minus 2u pi of t, g of t minus pi. Okay, that is the effect of this thing right here. It's a shift in the time domain. And then I have the other one, same thing. The table can, of course, help you with this, but you have to make sure that you can interpret it properly. Okay, same thing. This exponential here is resulting in this shift right here. So now I just need to figure out what g of t is. We have an expression for it there. It's the inverse Laplace transform of 1 over s times s squared plus 1. And I've done the partial fractions, so that is the inverse Laplace transform of 1 over s minus s over s squared plus 1, and that is equal to 1 minus cosine t. So g of t is 1 minus cosine t. So now I can combine that information for g of t with this information here for u of t to write the final expression for u of t. U of t is going to be 1 minus cos t, that's g of t, minus 2 u pi. This is a little bit confusing. This is u of t. This is the spring displacement. Getting to this stage and then realizing that maybe I should have used something else for the spring displacement, but I wanted to stick. This is the step function at t equals pi. Okay, so that is there, and then we've got 1 minus cosine t minus pi, and then I've got plus u2 pi t 1 minus cosine t minus 2 pi, and we are done. Okay, so we've gone through the words carefully, taking out all the information, developed the initial value problem, then used the Laplace transform to solve the initial value problem. Question 8. Okay, we've got a system of 2 first order differential equations. So you want to be, I mean, this is, we've typically used the capital letter A for that matrix. So this looks like this. And I want to just be, you wouldn't have to do this yourself when writing out an exam, but what I want you to do is remember and be clear that x prime, like that, is a column vector that looks like this, x1 prime and x2 prime, and that x is also a column vector looking like this, x1 and x2. So this is a statement of 2 first order differential equations when I have the matrix A being this thing here, 2 minus 1, 3 minus 2. So we want to find the general solution. To do that, we need to find out the eigenvalues and the eigenvectors of A. So to find the eigenvalues, I'm going to take A minus lambda I. That's going to give me 2 minus lambda minus 1, 3 minus 2 minus lambda, and then I will take the determinant of that. So the determinant of A minus lambda I is going to be 2 minus lambda. I see what I did. Okay, so I'm going to do it this way. 2 minus lambda minus 2 minus lambda minus 3, so that's going to be plus 3. Okay, so I figured out the determinant, and then I'm going to set that determinant to 0 and find the values of lambda. Those will be my eigenvalues. So I simplify this a little bit, and I get lambda squared minus 1, and I set that equal to 0, and then that tells me that my eigenvalues are lambda equals plus or minus 1. So I'm going to have lambda 1 is equal to 1 and lambda 2 is equal to minus 1. So those are my 2 eigenvalues. Those are my eigenvalues. All right. So then for each one of those eigenvalues, I need to find the corresponding eigenvector. So I'll do them one at a time. I'll take the first eigenvalue, lambda 1, equal to 1. I will write the matrix A minus lambda I for lambda equals to 1. So I'm going to substitute in here for 1, and I'm going to get 1 minus 1, 3, and minus 3. And then I am going to solve x1 equals x2, when does that equal to 0? And looking at this right away, I can see that this means that x1 is going to be equal to x2, and therefore 1, 1 is the eigenvector. Okay, then I look at the next eigenvalue. It is this one here. And I write out 2 minus minus 1, and minus 2 minus minus 1, and 2, and that's going to be equal to 0. And then I can see from that that 3x1 is equal to x2, and I get 1, 3 is the eigenvector. Okay, once I have the eigenvalues and the eigenvectors, I can easily write down the general solution. So the general solution to this system of two linear, homogeneous, constant coefficient ordinary differential equations is the following. And that just because it's popped into my head right now. On our exam, we're not going to have systems larger than 2 by 2. So it's going to be quite straightforward to find the eigenvalues and the eigenvectors and whatnot. It won't be a mess of linear algebra. We're going to keep them for testing purposes to the 2 by 2 case. Okay, so we have a general solution then, that x of t is going to be c1 e to the lambda 1t times the corresponding eigenvector, and then we have c2 e to the minus lambda e to the lambda 2t and its corresponding eigenvector. Okay, so this one here is lambda equals minus 1, and this one here, I called that lambda 2, and this one is lambda 1 is equal to 1. So that is the general solution of the differential equation. Because I've had some questions about this, I just want to make this clear. This means that x1 is equal to c1 e to the t plus c2 e to the minus t, and x2 is equal to c1 e to the t plus 3 c2 e to the minus t. Okay. So it's a way of representing both solutions using vector notation. Okay. All right, so we've got the solution. Now we're asking what is the type and stability of the critical point. So all the ones that are coefficient homogeneous with constant coefficients have a critical point at 0, 0, and then the type and stability are determined by the eigenvalues. So here, what do we have here? We have two real distinct eigenvalues. That's our, there's 3 possibilities. We could have 2 real distinct. That's the case we're in. That's one possibility. We could have 2 real and the same. So that would be lambda 1 equals lambda 2 equals 3 or something like that. And then we could have a complex pair. That is our only choices. So you should know what the stability and the type of the critical point is in all 3 cases. So we're in the 2 real distinct. So that means it's a saddle point. Okay, and we got to be careful here. They're real and they're distinct, and they have opposite signs. Okay, basically it means in one case you're going to be the function is sort of along one eigenvector you're going to be increasing, and on the other eigenvector you're going to be decreasing that saddle point. So it looks like well, you could look up on the internet what a saddle point is, but it does look look like the saddle that you would put on a horse. Okay, and it's unstable. you sort of imagine yourself putting a drop of water on a horse's saddle, and it will, if it just moves a little bit to one of the either sides where the slope is negative, it runs off to the side. So it's not stable. Okay, and then we're going to sketch the phase diagram. So we could let me try and make it sketch the phase diagram. So we know what are the eigenvectors. That's going to assist us in sketching the drawing here. So I'm going to draw here. This is the line corresponding to y equals 3x for this eigenvector here. So that is going to be this line here. It's sort of steep like that. And then I have another one, the line for the eigenvector 1, 1, that is x equals y. So here, this is a graph of x1 versus x2. So let me say it this way instead. X2 equals 3x1 for this one, and x2 equals x1 for this one. So I'm dotting that in. Then I put the arrows on which direction am I going, and I'm looking up, and I'm seeing here on this one here, as t increases, this thing is going to be increasing, and then this one is going to be decreasing. Okay, so I have my arrows like that here. That's for positive values of t, and then for negative values of t, of course the opposite thing happens because it's an exponential. Okay, and similarly here, for positive values of t, I am increasing like that, and for negative values of t, I am decreasing like that. I can also, if I like, compute some values. Oops, let's get that back. Compute some values. I could pick some values x1, x2, and then I can compute x1 prime, x2 prime, right from the system of equations. So I've made a few calculations. I sort of select x1, x2 equal 0 and 1, and then I can compute that x1 prime is -1 and x2 prime is -2. So I can use a variety of points here to help myself see what's happening. So I then compute this one, and I get those two values. I computed this one, and I got these two values, and I computed this one, and I got these three values. So I get some help with what's going on here, but it's fairly, actually, then with a few points, it's easy to see that it's going to be kind of going like this in here, and over here it's going to be basically going like this, and over here it's going to be going like this. You're not going to cross those I guess the final one, do it properly here. We're going like this. Okay, you're not going to be crossing those lines established by the eigenvectors. Okay, so that is question 8. Well, I guess question 9 is a continuation, so we get to keep going with this system. Let us see what the next question is. Okay, no, continuation. Please don't miss something like that. That means we're dealing with the same system that we have just been dealing with. So if you don't want to miss something like this and then get confused about what's going on. So careful reading. So we are now being asked for a particular solution with the initial conditions. Not a problem, because we have the general solution. Here it is, C1 e to the t 1 1 plus C2 e to the minus t 1 3. Okay, and we have that we have the initial conditions. I'll write them in the vector format right now, but that's what our initial conditions are like. So now it's simply a matter of plugging those numbers in and solving for C1 and C2. So I know that x of 0 is equal to c. Now I'm putting t equals to 0. I get c1, and e to the 0 is 1. So I have 1, 1 here. And then I have c2, and I put t equals to 0 here, and I get 1. So that goes away. And then I know that that is supposed to be equal to 1, 0. Because I got told that. I mean, that's the initial conditions. That's where this is coming from, the initial conditions. Okay, so now I have two equations and two unknowns. I find it easier maybe to write this out in this manner. C1 plus C2 is equal to 1. That's the first row here, if you will, and then the next one, C1 plus 3C2 is equal to 0. So two equations, two unknowns. This just keeps happening, and I solve those, and if I don't make a mistake, I find out that C1 is 3/2 and C2 is -1/2. Okay, so then I can write out the particular solution satisfying those initial conditions. Here it is. Okay, keeping going with the same question, by eliminating one of the variables, show how the above first order system can be written as an equivalent single higher order differential equation. Okay, so this, we had a question, I think, I don't know if it was this exact question, but basically it's the same kind of question because it was a 2x2 system. We had this question on a quiz. I think it was quiz 8. And it was actually fairly poorly done. So if you did not get any marks for this question on quiz 8, please pay careful attention to this question and make sure that you can do this, because we should be able to, we are supposed to be able to, and we need to be able to take any higher order, a second order ODE, and turn it into two first orders, or take a third order ODE and turn it into three first orders, and we need to be able to go backwards too. So it doesn't just work one way, we can go forwards or backwards. In this case, we were given it as a system of two first order. Now we're going to turn it back into a second order differential equation. Okay, I mean, it says here higher order, but that's, I mean, there's two first order, so we're going to be turning it into a second order, which is indeed a higher order. Okay, so I'm going to just write it out like this. This is the same, this means exactly what I've just written here. I'm just expanding out the vectors into their components. Okay, so I write it like that, and then that allows me to see that x1 prime, now I'm doing matrix vector multiplication, that's going to be 2x1 minus x2. Okay, so I'm figuring out x1 prime is this row times this column. And then I do x2 prime equaling to 3x1 minus 2x2. Okay, now what I have to do is eliminate either x1 or x2. I'm going to eliminate x2. So I'm going to get a differential equation in terms of x1 double prime. Okay, so the first thing I'm going to do is, I'm thinking of that. So I'm thinking, okay, my idea is to eliminate x2 and x2 prime. Then I'll only be left with x1s, and I will have accomplished the task at hand here. So I'm needing to eliminate x2. So the first thing I'm going to do is take a look at this one here, this equation here. So let's take a look there. That is telling me that I'm moving x2 to the other side. x2 is minus x1 prime plus 2x1. Okay, that's going to allow me to get rid of x2 wherever I see it by replacing it with this. What else do I know? I know what x2 prime is. Okay, over here, I can take the derivative of this one here, and I get x2 prime is equal to minus x1 double prime plus 2x1 prime. Okay, I'm happy to have these things here, and then I in fact know what x2 prime is. Right? Here I have x2 prime, and here I have x2 prime. Okay, so I can now get rid of, I can use this thing here, and I can get rid of the x2 prime on the left hand side. So I'm going to do that. Let's see here. I'm going to do that this way. So I'm taking this statement right here. I'm saying, okay, I notice x1 double prime. plus 2x1 prime. That is equal to, I just reversed the order, x2 prime. But what is x2 prime? I know what x2 prime is. It's this thing right here. So x2 prime is 3x1 minus 2x2. But I'm trying to get rid of x2 and x2 prime. So now I've accomplished getting rid of x2 prime, but I have here an x2, and I'm going to get rid of that using this statement right here. Okay, so x1 double prime plus 2x1 prime is equal to 3x1 minus 2. And now I want to get rid of x2, and that is minus x1 prime plus 2x1. There it is. So now it's a simplification problem. I've gotten rid of x1 and x1 prime, and I just need to put everything together in a simpler manner. So I'm just going to do that. 2x1 prime equals 3x1 plus 2x1 prime minus 4x1. And then that's, let's see, 3 minus 4. So I have 2x1 prime minus x1. So now I'm looking at that, and I'm putting things together. Oh, isn't that nice, right? And so I get minus x1 double prime equals minus x1, and that means that x1 double prime minus x1 is equal to 0. There it is. Okay, I have now converted the system of two first order ODEs into a single second order ODE. Make sure you can go both ways. Okay, we're on to the final problem. This problem is time consuming. It is a series solution. I will be asking a series solution problem on the final exam that we're having this year. Okay, and I'm gonna, this is the one method that we have to do things that are much more complicated, for which none of our other methods will work. So there's a variety of things ancillary to this kind of a question that you should make sure that you know, and that is being able to determine if you're at an ordinary point or at a singular point, and then understanding what to do if you have a regular singular point or an irregular singular point. Okay, this question actually is does not, in fact, even ask you that, so you can proceed, I guess, in some sense. I mean, I guess in some sense, you're going to be making the assumption that it's at an ordinary point, okay, because it does not specify. Okay, so is it linear or nonlinear? Okay, so let's take a look. I see that both of these functions here are in terms of x alone, so this is linear. And in fact, I'm looking now at those functions a little bit more carefully, so I could potentially label this function here p of x equals to x squared minus 1, and q of x is equal to 2x. And I can see that, in fact, every point is an ordinary point. That's a nice feature. Okay, next point, I really want to make this super thing. Read the question. I remember when we marked this question, a lot of people tried to give a general answer, and that is not being asked for. You're only being asked to provide a series solution up to the x to the 4 term. That means your solution to this should look like this. a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4. That's it. You don't have to solve the recurrence relation and get the general term. That's a major feature, because you can go by, once you're as you're going to see, we're going to be able to find a1 and a2 from the initial conditions, and then it's going to be an easy matter to determine the next three from a0 and a1. You do not have to find the general term. So be careful. Read the question. If it tells you to just do a small portion of the of the thing, just do the small portion. Don't try to do the general problem. Okay, so how do we, on all of these series solutions questions, we are going to start by assuming a power series. In this case, we're at an ordinary point, so it's all we just assume this power series right here. We take the derivative. This is the same for every problem that we do with the series solutions. I've done this a bunch of times in some of the previous videos, and you should make sure that you can do this. So this is always the same. Doesn't matter which, so nothing is specific to this differential equation at this point. Okay, so that is always the same. So now I substitute into the differential equation. So I've assumed the series solution, I've calculated the first and second derivatives, and now I substitute into the differential equation. And so that'll be y double prime plus x squared minus 1 y prime. So I'll do that in two pieces, x squared times y prime minus 1 times y prime plus 2x times y. Okay, be careful with the indices. It's critical to getting the right coefficients on your power series that you are extra careful with the coefficients. Okay. All right, next step here is we need to adjust the indices so that they are all going to be starting at the same number. And so that number is going to be in the end n equals 2 to infinity. So what I'm looking at, I need a variety of things so that I can start to write out the solution here. I need these to be the same for all the sums so that I can put them together. And I also want to work with the I'm just going to pause here momentarily, with the same powers of x. Okay, so let me show you what I mean here. I'm going to adjust. Here we go. I'm first going to be adjusting on the powers of x. So I'm going to notice that this one is x to the n. However, okay, no, forget it. I'm sorry. Let me just pause momentarily here. I'm going to first do a little bit of. I'm going to take this and multiply it in here, and then I'm going to take this and multiply it in here, and I'm going to watch what happens to the powers. And I'm at the same time going to change the indexing on this one here. So I'm going to replace on this one here, n is going to n plus 2. Okay, so I'm going to do that on this first sum, and then I'm going to just deal with the adjusting the powers of x here. Okay, I'm trying to, let's see what happens here. Okay, so here is going to n plus 2. So I'm here n plus 2 equals 2 to infinity, and I'm changing n to n plus 2. So this is n plus 2. This is n plus 1. This is a to the n plus 2, and this is x to the n. Okay, x to the n. And then here, I'm going to be, the sum equals n equals 1 to infinity, n a to the n x to the n plus 1. And then here, I'm going to be not changing this one at all, n a to the n x to the n minus 1. And then on this one, I'm moving that into the inside. It's still n equals 0 to infinity, a n x to the, there's a 2, to the n plus 1, and that is equal to 0. Okay, so n plus 2, this here, n plus 2 equals 2 means that n is equal to 0. Let me, in fact, I don't want to, that I can, I'm thinking that is same as n equals 0, subtracting 2 from both sides. Okay. So now I see I've got x to the n here, and I've got n plus 1 here. I've got n minus 1 here, and I've got n plus 1 here. So I wish to change the indexing so that I've got them all powers of x to the n. So I don't need to do anything to the first one. So this is going to be the sum of n equals 0 to infinity of n plus 2, n plus 1, a to the n plus 2, x to the n. That's just copying this from here. I wish this one now to also be in powers of x to the n. So I need to adjust n to n plus 1. I have to do this. N to, okay. So then this one here will become, that's what I'm doing. This one here is going to become n equals 2 to infinity. This will be n minus 1, a to the n minus 1, and then this will be x to the n. Similarly, this one is going to be, that's a minus. This one here is going to be n equals 0 to infinity of n plus 1, a to the n plus 1, x to the n. Okay, you can see that I moved in opposite directions. So you should make sure you see how this one has gone from 1 to 2, and this one has gone from 1 to 0. That's because this is plus 1 going to n, and this one is minus 1 going to n. So if you can clearly see how to change the indexing to line these things all up to be powers of x to the n, that is a good thing, because that is the secret at this point to getting the right recurrence relation. So now I'm here, and I've got 2a to the n minus 1, x to the n, and that's all equal to 0 still. So similarly, this one's gone from, right? And then this has gone from 0 to 1. Okay, so you want to make sure you understand how to just, it's just working with the summation notation. Okay, now I've got them all in powers of x to the n. So I can very easily add these together. So I'll just highlight what the important feature is right here. All of these things, all the sums are now expressed, so I have in powers of the same exponent. They're all x to the n. Now I'm looking at the lower index on these sums, and I see that I've got here 0, 2, 0, and 1. 0, 2, 0, and 1. So I can start them all at 2. I want to make them all the same. So I'm picking this largest one, 2, and in order to do that, I'm going to write out for this one, I'm going to take out the n equals 0 and n equals 1 separately, and then leave the rest. So here I'm taking out the n equals 0 term. So when n is 0, I get 2 times 1 times a to the 2. And then I get x to the 0, which is 1. So this is 2a2. That is the n equals 0 term from this sum that I'm looking at. Let me get the whole thing. I am looking at this one right here. Okay, and now this is the n equals 0 term, and then the n equals 1 term looks like this, 6a3x, and then I have the rest of them starting at 2, okay, which I'm going to put over here. And equals 2 to infinity, and then I have the rest of them. There it is, n plus 2, n plus 1, a to the n plus 2. That is this thing right here, and it's going to be times x to the n, but I'm going to add some more things here, so I'm x to the n. Okay, so there's going to be something here times x to the n, and that now I've dealt with that first term. I'll try to use the colors here to make it as clear as possible. Now I'm going to look at the second term, this one here. Okay, that one already has starting at n equals to 2. So we don't need to do anything. We can simply add this plus n minus 1 a to the n minus 1 here. Okay, next one, this one here, is starting at 0. That means I need to take out the n equals 0 and n equals first term, which I will do like this. That will be minus a1 minus 2a2x. And then the rest of them are going to have to be here, which is going to be this term right here. That is going to be minus n plus 1 a to the n plus 1. Okay, the minus sign is here. Sorry about that. I've sort of not got enough space, but this is coming right here. And then I look at the final one. It's starting at, let me change the color. That is starting at n equals to 1 right here. There's no n equals 0 term. So I'm taking out the n equals 1 term, and that is going to be right here, 2 a naught x. And then I have the rest of them here, plus 2a to the n minus 1. And they're all times x by xn, and still the whole thing is equal to 0. Okay, so now we have the fact that everything on the right-hand side, the constant term, the linear term, the quadratic term, the cubic term, every single term of the polynomial on the right-hand side is 0. That means every term on the left-hand side of the polynomial has to be equal to 0. So I simply gather up the constant term. Okay, there's going to be no constant term. Okay, I sort of randomly got a question happening here. Okay, so there's going to be no constant term because from the summation here, because it's starting at 2. So that'll be x squared, will be the first one. So for the, I get here, for the constant term, I'm only now looking here. And what is the constant term? The constant term is 2a2 minus a1. And that's going to have to be equal to 0. Then I'm looking at the linear term also coming from here. And that's going to be 3a3 minus a2 plus a naught is equal to 0. Okay, that tells me what is A1 in terms of A2 in terms of A1, and it tells me what is A3 in terms of A2 and A0. Okay, so let's think for a sec here. Do I know what is A0 and what is A1? Yes, I always know. I'm going to scroll back and make a note of that. I always know. Let us take a look here. I imagine that I have this thing here, okay? And I ask, what is y of 0? Well, y of 0 is when x is 0. So that means that, let me even just write it out. So y of 0 is this sum, n equals 0 to infinity, a n x to the n, evaluated at x equals 0. That looks like this, a naught plus a1x plus a2x squared plus dot dot dot, evaluated at x equals 0. So that is a naught. Okay, similarly, by exactly the same thing, y prime evaluated at 0 is a1. Okay, so I'm going to write those two things here. So, I mean, without even, this is always the case. This has nothing to do with this specific differential equations. It's always the case that a naught is y of 0 and a1 is y prime at 0. So, I mean, I'm got told in this problem to find up to term 4. Without even doing anything, I, in fact, have identified what a0 and a1 are. There are those two things here. Now, down here, I've got a mechanism for figuring out what a2 is in terms of a1. Right here, I know that a2 is equal to 1/2 a1. So I know that is equal to 1/2 of y prime at 0. Here I know that a3 is 1/3 minus a naught plus a2, and that is going to be minus 1/3 minus y at 0 plus 1/2 y prime at 0. Okay, the only remaining thing for me to do is find out what a4 is, and I find that by using this expression here. Okay, so I'm going to write that out. A4 is equal to 3a3 minus a2 minus 2a1 over 4 times 3. And that means that a4 is equal to y at 0 minus 2y prime at 0, all divided by 12. Okay, so now I've got all of the coefficients up here. I got a0 and a1. Tick. I need to have a2, a3, and a4. I don't have to solve the recurrence relation. I'm not asked to do that. So I've got. I'm just going to change the color because I'm going to put it in red here. All the things I wanted. So I've got a0 and a1, and down here I've got a2. That is a2. There it is. I've got a3. There it is. And I've got a4. And that's it. I can stop. I don't have to set up any sort of general term an is equal to anything because I was not asked to do that. Okay, so now here it says find the general solution, again up to turn 4, according to the initial conditions, y of 0 equals 2 and y prime of 0 equals -1. So now this is just an easy substitution problem. I've been given the initial conditions. So let me just do this. I know that from the previous part that y of t is equal to y of 0. Okay, so y of x, actually I used x as the independent variable. Y of x is y of 0 plus y prime at 0 times x, true for every one of these things, plus 1/2 y prime at 0 times x squared, plus 1/3 minus y of 0 plus 1/2 y prime of 0 times x cubed, minus y of 0 plus 2y prime of 0 over 12 times x to the 4. I got the bracket here. I want this bracket. I don't want this minus. Okay, so now it's just a matter of filling in what I've been told. That is y of 0 is 2 and y prime of 0 is -1. Okay, I do that and I find out that the first four terms of my series solution, I'm going to just do it in terms of x, look like this. 2 minus x minus 1/2 x squared minus 5/6 x cubed plus 1 over 24 x to the 4. And I've done what was required. I've found the series solution up to the fourth term. So I mean, this sort of looking back to what you probably did in calculus 2, I mean, this would be the Taylor polynomial of degree 4, and then we would, of course, this is not a complete solution because the complete solution is an infinite series, so there's some stuff missing here, but we could bound that, and we could just use this polynomial to as an approximate solution to that differential equation. Okay, so that's another one of the more time-consuming problems because there's a lot of careful algebra that you need to do to be able to get the solution. But that is it. Okay, 10 problems on the final exam. It'll probably be something similar. As I indicated to you in my last announcement, I will be sending a more clear announcement about the exact topics on the final exam, how many questions, that sort of thing. I'm going to make the exam, I'll be sending you that to you shortly, and I'm also going to make the exam a little bit shorter. So this exam, 3-hour exam, I'm going to endeavor to make our exam this semester 2.5 hours long. That's to give 2.5 to 2 hours and 45 minutes. That's to give you time to write the exam and do the uploading to CrowdMark in the 3-hour time frame. Okay, so I'm going to expect that that the uploading will be done at the 3-hour mark. There won't be any time after that to upload. The reason for this is that some people have more than one exam on a day, and we need to keep within the exam period. So look for some announcements coming about that, but that is now, we have now concluded all of the lectures for this semester. Good luck on the final exam, and please email me if you've got questions. Thank you.